Hello everybody. This is going to be your last video on the immune system. We're going to look at your humoral immune responses, and then I'm going to walk you through your full immune system response to something like the flu. And after we've gone over everything from initial infection through all of our barriers and defense mechanisms from initial infection to the end of it. And then we'll go over some other information like diseases that are pertinent to know. Right? So in your last video, when we started talking about your adaptive immune system, we were talking about B cells and T cells. So we have covered basically what the military and your Marines are doing. Those were your T cells. Right? Now we are going to check in with the CIA and see how our B cells are doing on their intelligence and that sort of thing. Right? So if you remember, B cells were the other type of lymphocyte that you guys needed to know, and they go to their boot camp in the bone marrow where they mature, and then they are shuttled off to lymph nodes where they become immunocompetent. Right? What happens during a humoral immune response is there's going to be an antigen challenge, right? There has to be some kind of first encounter between an antigen, an identifying protein from a bacteria or something, a name tag from a protein, and a naive immunocompetent lymphocyte. So there's going to be that first time meeting sometime, right? Usually this is going to happen in a lymph node, maybe in the spleen. Not all the time, but that's where this usually happens. If that lymphocyte is a B cell, because we know B cells have been trained to identify antigens and accept them, right? If that lymphocyte is a B cell, the antigen is going to provoke a humoral immune response. That means that your B cell is going to begin making antibodies, which are quite possibly the most important complement protein, right? Or immunoglobulin, right? Antibodies are secreted by B cells. It's their job. And there are 5 different classes of antibodies: IgM, IgD, IgG, IgA, and IgE. The kind of illnesses and bacteria they target are going to depend upon protein complexes and which type of antibody it is. This gets into biochemistry and basic knowledge of chemistry for what will interact with other things on a chemical level. Right? So, your B cells are going to be activated when an antigen binds to its surface. Right? So there's going to be an antigen that is introduced to a B cell eventually. Right? The B cells are going to be activated when that antigen binds to its surface receptors, and it can cross-examine or cross-link them. That receptor, if you notice here, you've gone from your B cell just accepting it to kind of starting to poke in. This is called endocytosis. It's sort of like when a cell drinks, is how I would explain that to my high school students. But endocytosis is not as extreme as phagocytosis when a cell goes full Pac-Man on things. This is just sort of like slurping that antigen through the side of the cell. Just like, shoop. Right? Just taking it in. But you're going to have receptor-mediated endocytosis of your antigen receptors, right? And this is going to stimulate this specific B cell. It's going to grow, so it's going to get bigger, and then it's going to form clones of identical cells that have the same antigen identifiers inside them. and it's going to create the same antigen-specific receptors, right? Usually a T cell helps out here. So a helper T cell will find a B cell and introduce the B cell to this antigen that it was just introduced to. Your B cell is going to create a receptor that can attach to that antigen, and then it is going to start growing and dividing into clone cells that can also create receptors that will bind to that antigen because it was given the antigen of the bad guy. This means that your B cells, they were basically given the proteins off of the outside of a threat. They have taken them inside internally, and internally they are chemically figuring out how to build proteins that match that antigen and will stick to them. Like, their job is to build little mini receptors that will mob the pathogens and just cover them because they are covering the bad guy's name tags. That is what an antibody is. An antibody is purely a little immunoglobulin protein that is created and built to attach to the pathogen's receptors, right? And because it is attaching to all of the pathogen's antigens, or name tags, this is going to flag the pathogen for natural killer cells and other cytotoxic T cells to notice, mob, and kill. Sometimes, if enough antibodies can attach onto a pathogen, they will either burst or tear apart the pathogen or just weigh it down and kill it. But most of the time, antibodies serve to stick pathogens together, weigh them down to slow them down, and flag them so that your cytotoxic T cells and natural killer cells can see them or notice them easier and then kill them. That is the purpose of antibodies, and the job of your B cells is to research antigens, make antibodies, and then remember how to make the antibodies. So once these antigens or antibodies have gone through through endocytosis, your B cell is going to grow and then start making clones of itself that will all make more antibodies, right? Your B cells are going to become plasma cells, or these clones of your B cells are going to become something called a plasma cell. Plasma cells are the clones that make and secrete the antibodies at high levels into your bloodstream so that they are circling around your bloodstream to help cure you of any viruses, right? So plasma cells are going to secrete antibodies as a response to respond to that surface antigen or specific antigen. So these plasma cells are super efficient at their job, right? They secrete these specific antibodies at a rate of about 2,000 molecules per second for 4 to 5 days. That is their job, and that is fully what they have evolved to do. They literally have been cloned and created, and they are going to pump out 2,000 antibodies a second for 4 to 5 days. That's what their job is. It's what they do. Right? So if we're going to talk about the fate of these clones, because they are working so very hard to make these antibodies for you that will help you when you're sick, right? We need to talk about the fate of these plasma cells and clones. So the fate of the clones. They're secreting the antibodies. These antibodies are going to circulate in the blood or the lymph. They bind to the free antigens or free-floating antigens from pathogens that are around, and they are going to mark the antigens for destruction. All of these plasma cells, these clone cells, are eventually going to die after those 4 to 5 days. They work themselves to death. They use all the energy they possibly have to burst and to like make all these antibodies and burst through that production to then die of exhaustion at the end of the process and undergo apoptosis when they're out of energy, right? Clone cells that do not become plasma cells, so the ones that did not become the little factories for antibodies, become memory cells. So these are your long-term CIA agents. They weren't used as a one-off spy or informant like the plasma cells were. They become memory cells, and these are your retiring CIA member friends. Right? These guys are going to become memory cells. They provide immunological memory. So they are going to remember the specific virus or whatever it was that caused you to be sick in the first place. They are going to remember that. And the next time you are infected with the same virus, the same illness, these B cells will wake back up and mount an immediate response for future exposure to the same antigen. Right? That is the entire purpose of your humoral immune system. These B cells are going to help create the antibodies that will help bring down the cells that are infected with that virus or those other viruses. And the B cells that don't kill themselves from working to do this are going to stay in your body for potentially up to the next 60 years. They have a long lifespan. And remember that illness until you die. Or they die when you are elderly. Right? So that is your B lymphocytes and antibodies responses, right? So you have this 4-chain model of an antibody structure here. They're going to find the antigen and attach to them. This is why you have 5 classes of antibodies, right? These are your 5 classes. One of them is this dimer shape. You have a monomer one, pentamer with 5 points, right? Right. Right, so some of these guys are going to be cloned and selected as plasma cells to make more antibodies. Some of them are going to become memory cells that will remain in your body for as long as they can, right? This creates 2 different potential waves of response time for your body, right? You're going to have the first time you catch a specific flu, so the first time you get sick with something, and then you're going to have the next times you're exposed to the same illness, right? So there's either going to be a primary immune response or a secondary immune response. Your primary immune response happens the first time you are ever exposed to a specific antigen. So the first time you were ever exposed to H1N1 swine flu, right? It didn't exist before 2009, and now all of a sudden, in 2009, it's sweeping through the country because it's a new mutation of the flu and it's hitting people hard. You're going to have a primary immune response to this, right? Because of the need to introduce B cells to this new antigen, there is going to be a lag time of response. That means you were headed to work in 2009 when swine flu was happening, 11 years ago, right? You got into an elevator with, coworker Bob. And coworker Bob sneezed and exposed you to H1N1. And you both went about your day because he sneezed in an elevator and you were still breathing because it's what we do. You've been exposed to H1N1. You won't show signs of being sick, and you won't have a proper immune response toward that for 3 to 6 days. It's going to take time for that flu, H1N1, to fully set up in the back of your throat and for you to feel sick and then have a full-fledged immune response to that. Because it's going to take 3 to 6 days for all of this information to trickle down all of the systems that we've talked about to get to the B cells finally. Right? But that means that your body's peak levels of plasma antibody production are going to be reached about 10 days out. Right? And different illnesses do have different incubation periods, so this is a generalized response time, right? For faster illnesses, you're going to be closer to the 3-day lag period, and then you'll have like the peak period closer after that. For other illnesses, 6-day lag period with the peak 10 days later. For COVID, we're giving a 2-week or a 14-day window where you are contagious and can spread it but don't know before you get symptoms. Right? So that's why we've been warning people for COVID now in 2020 for a 14-day or 2-week window for quarantine. Other illnesses are shorter, right? But you're basically going to have peak levels of antibody production around day 10 if we're talking about a normal flu, right? Or a normal illness. And then after that, your antibody levels are going to decline, just slowly decline. Right? But your body remembers how to make those H1N1 antibodies. Your body remembers 11 years ago, right? So you had your primary immune response to H1N1 11 years ago when it first happened. If somebody were to sneeze upon you now and you weren't wearing a face mask for whatever reason in 2020, right? If somebody sneezed upon you and exposed you to that same H1N1 flu virus, that is called a secondary immune response because it is not the first time you've ever been exposed to it. So your body goes into, I've seen this before mode, right? Which is your secondary immune response. So secondary immune responses occur on re-exposure to the same pathogens that you have already been exposed to, right? Basically, within hours of coworker Bob once again sneezing upon you, this is the second time you've seen H1N1. Your body, upon you inhaling that flu virus and it starting to infect your cells, your body can recognize it within hours. Hours. We're not talking up to 6 days to figure out what it is now. Your body already has the wanted posters memorized, right? So your body and your memory cells are going to start responding to that re-exposure within hours. Your antibody levels against the specific viral infection are going to peak 2 to 3 days after your exposure to it, and when they peak, they're not going to be at the normal levels that they were during your first response to it. Your body already knows what this flu is capable of, so you're going to have exponentially more antibodies produced and pumping out for this secondary exposure. You're going to have much more of a stronger secondary immune response, right? So antibody levels are going to peak 2 to 3 days after your exposure, and the antibodies are going to bind with a greater affinity. Your body has gotten more efficient at making these antibodies, and it's made it better at being able to attach to those antigens. So the antibodies are going to work even better and attach more, right? And then your antibody level for this illness is going to remain high against this illness for any time span between weeks to months. Because your body is like, oh no, we've seen this before. We already know what happens and what it can do. Protect ourselves from this more permanently. Right? So that's what's going to happen the next time you are exposed to those exact same flus anytime again. Right? And that's the difference between a primary immune response and a secondary immune response. Right? So this now gets into how you mount this immune response and how you get the antibodies. This can be debated amongst some things. Right? So we've been talking about incubation periods and that kind of thing. This is what happens when we start talking about our healthcare system and where things are going to get sick or people better, right? We have to talk about how you acquire humoral immunity to different illnesses. And the responses vary There are 4 basic ways. I believe I gave you this chart in your note-taking guides. This is a happy little picture version of the same chart if you prefer images instead of words. Both of them have the exact same information on them if you know how to read them, right? So you have to start discussing how you get your humoral immunity and if it can last. Because there is a difference between having active immunity, which means your B cells are working and doing their job, versus passive immunity, which means your B cells are skipped and you're getting the benefit of having a humoral response, but your body is not actually doing any of the job. Right? So we're going to talk about active immunity first. So, active immunity. Your active humoral immunity is what's happening when we make your B cells encounter the antigens themselves, and your B cells are the ones that have to produce the specific antigens against, or produce the specific antibodies against the antigens from the pathogens, right? Your body is doing the work for active humoral immunity. And there are 2 ways that we can make your body do the work for active humoral immunity. You have a natural method and an artificial method, right? Natural means it's naturally acquired, all natural. You got sneezed on, you got the infection, you got sick, right? So natural, active immunity is the response to the bacterial or viral infection because you got sick. Someone sneezed on you, you didn't wash your hands after using the bathroom, and then you touched your face. Something like that happened. You got sick, right? The most natural, active thing your body could do, you got sick, you exposed yourself, you're done, right? On the flip side of things, if you don't want to get sick with something, right, or we deem that getting that illness has too many risks involved, for example, measles. We don't normally think about measles as not being a common illness, or we don't really acknowledge it as being severe, but realistically and statistically, measles killed 1 in every 1,000 children that it infected. And I'm positive, if you're talking about your child, if you're a mother, most mothers and women who know that statistic do not want to take the chance that their baby is that 1 in 1,000, right? Additionally, for mumps, because one of the first vaccines you will ever get is your MMR. Additionally, for mumps infections, if you're not exposed to mumps when you're younger, if you are a gentleman and you are exposed to mumps later in your life post-puberty, the tissue in your testicles is a great deal like your salivary glands, and I know that sounds weird, but it's true. And catching the mumps post-puberty can actually lead to infertility in men. Like, that can affect your sperm production and ability to have babies. Rubella, the R in the MMR vaccine, it's a little bitty flu when you're young and a baby. It's annoying. Nobody wants their child to be sick. But the catch and problem with rubella is, yeah, it's not that harmful if a toddler catches rubella, but if a pregnant mother is exposed to rubella, that can actually travel to the fetus and then cause the fetus to either grow blind or deaf. So if you choose not to vaccinate your daughter, and then your daughter gets pregnant later in her life, and she and baby are exposed, when baby's a fetus, to rubella, because grandma chose not to vaccinate her daughter, the baby may be born deaf and blind. This is why having the MMR vaccine is one reason why deafness and blindness is not as prevalent in our society as it was a few hundred years ago. And because we are alive in 2020, and we've never known the kind of world that was in the early 1900s or 1800s when these were more commonplace illnesses, We've never seen that effect. We've lived in our comfortable first world societies in America since then. So we take this for granted, right? So we have created, so you don't have to risk these downsides to these viruses, artificial ways to make your body do the work to protect you. The artificial acquired active immunity is a vaccination, because vaccines, which only protect you from viruses, are dead or attenuated pathogens. That means either we have taken the virus and killed it, and we are literally injecting a sample of dead virus into you for a vaccination, or attenuated means they have taken the virus shell and they've taken all the genetic information out of that viral shell, and they're putting the empty husk of a virus in you. That's what an attenuated vaccine is, if you've ever heard that term before. So with artificially acquired immunity, we have figured out this artificial way to put the virus inside us so that we can make our own B cells gain immunity toward it. Essentially, the purpose of a vaccine is to spare you the symptoms of having a primary response to getting this first illness itself, but it's still giving you a sample of that virus, so you can you are provided with antigenic determinants that are immunogenic and reactive, so your body can get a head start on making those antibodies and building the memory cells to it, so that your body will already be prepared to mount a humoral response against that virus. That is the entire purpose of a vaccination. And some vaccines, like the MMR that I've just used as an example, the current rendition of the MMR was invented in the 1960s. Without looking it up off the top of my head, I believe it was 1964. It may be around 1962 or 1963. We've had, at this point in time, 60 years to, see the effects of the MMR vaccine. That one I would deem pretty safe. There's no reason to not consider that one, unless your child is allergic to something, right? Your kid isn't going to get sick from the MMR. If you want to call into question newer vaccinations, do your own peer-reviewed research, right? There are lots of new vaccinations. I am pro-vaccine, but some people disagree with some of them in place of others. But vaccinations on the whole spare you the downsides of the infection that could have been detrimental, which is why they are typically good, and viewed as good. Some people prefer not to get them. Most people would say they're very important and prefer that you do, right? And that leads us to passive immunity, right? How does this stuff work if your B cells aren't the thing doing the job and aren't the thing doing the work, right? What happens with passive immunity is your B cells are not challenged by any antigens. That means there is no immunological memory at all. Anything that you have been cured from via passive immunity, your body will not remember. Your B cells did not do any work, so your B cells are not going to build any memory cells and remember any of this. Right? No work was involved, that's why it's passive, but your B cells will not remember it. There are two major types, once again, for passive immunity. Natural passive immunity, probably one of the most natural things that can happen. Your prime example of this one is a mother breastfeeding her child, right? One of the good benefits of breast milk and breastfeeding your baby is that mom produces her own antibodies, right? Because mom has a fully functional immune system, and mom is going to give some of her antibodies to the baby through her breast milk. That way baby is going to have some sort of defense, and baby's little bitty immune system doesn't have to do the full job if somebody sneezes on mother and baby and exposes both of them to an illness. But baby can piggyback off of the work that mom's body does. Right? So mom's body will create antibodies for the things that she is exposed to, and she will share some of her antibodies through her breast milk with her baby. That is natural humoral immunity being passed from mother to infant. The baby's body will not remember how to make its own antibodies of whatever mom passed to baby. But for the meantime, while baby is breastfeeding and getting those antibodies from mom, baby will also have the humoral protection for it. Right? So this is mom naturally sharing with baby. The artificial method of this. We have concocted a few different ways to help with a couple of various illnesses. We have developed some medications that use these antibodies, immunoglobulins, and that kind of thing for specific illnesses to help people get over certain situations. A good example of this is Anti-Venom, right? You need antibodies against the venom if you are bitten by a rattlesnake. If you're walking down the Silver Comet Trail and you're bitten by a rattlesnake, you need rattlesnake antibodies because you were just bitten by the snake, right? When we inject, or when you go to the hospital and the hospital injects antivenom into you, that antivenom was collected from other snakes' venom, and we artificially created antibodies against that venom that they are injecting into you or giving to you as antivenom medication, right? So while they are pumping you full of the antivenom, which is going to stop and clot up the rattlesnake venom that was bitten into you, your body is going to gain protection from that a little bit, right? This means that for artificially acquired passive immunity, your body and B cells are not going to remember at all how to make antibodies against snake venom. It's just not going to happen with this method. But your protection against that venom is immediate. You went to the hospital and this is immediately helping you. But after a few hours, when these proteins naturally degrade in your body, that protection will end. So this protection for your artificial passive immunity is only going to last as long as the actual antibodies are put together and still in your body. Once you have reached the point where they are not, and they have degraded, you either need more antibodies, you need more like antivenom if you got this from Anti-Venom, or you may still die if you still have snake venom like coursing through your arm from the snake bite. Right? So those are your two methods of immunity here, active and passive. Right? There are a couple of other blips that we can look at with your immune system. Your intestines, for example, are lined with Peyer's patches. Those are part of the lymphatic system. That is going to be like a hub for your immune systems to double check the things that are being absorbed by your intestines, right? Mucus helps you. That's why you have a slightly different response from mucosal linings, because the mucus is going to help catch and neutralize pathogens that get into you, right? Yeah. This is also going to provide you with, and bear in mind, this immune responses that we have been discussing this entire time are defenses against bacteria, fungus, parasites, and viruses. So you're going to have similar immune responses to kill any of these defenses or invasion pathogens. It's just going to be which cells respond to it, right? So those antibodies that were IgE antibodies typically are reserved for helminths, allergy responses, asthma, or parasitic responses like eosinophils, right? T-cell cytokines can flush out parasites, and they will help those eosinophils because eosinophils deal with parasites, right? Natural killer cells fight viruses. With interferons, you have cytotoxic T cells, all that kind of stuff. It's just going to be which cells can respond to which threats, right? Who are you going to call? Which branch of the police force are you going to call? Are you going to call homicide or narcotics? Right? That kind of deal. So before we start talking about the way things can go wrong, I'm going to take you through your body being invaded by a pathogen, right, from start to finish. And I don't have a chart or a graph for this, so I'm going to talk you through that invasion point the first time from a scientific perspective, using all of our fancy terminology, and then the second time, more like a story time personality, right, or story. So pathogens can invade your body from a number of different reasons, right? Different strains of bacteria or different strains of viruses, like different colds and different flus, all have different characteristics and different surface antigens. This is why we don't just get one flu vaccine and we're done with it for the rest of our life, like we do with measles and like your MMRs, measles, mumps, and rubella. The flu mutates too fast for that. So we need to have a new flu vaccine every year for the new flu virus that has mutated every year. On the flip side of that, measles is pretty steady, so the same vaccine that we have had since the 60s still works, right? But multiple different strains of these pathogens are going to create different antigens. And remember, immunity was entirely based upon recognizing those antigens and name tags, right? So that means that if you are, just because you are immune to a regular flu, doesn't mean you can't get swine flu, right? Mutations, both in your body and in their body, can change this recognition. So you have to consider genetic genotypes and phenotypes and random genetic mutations and that sort of thing. Genetic recombination as well for when you have children. So you may be immune to one thing, but because of you and your partner's genetics combined to make your child, your kid may not be the same. Your kid may have a weaker or stronger immune system than you do, right? It's the luck of the draw with genetics. And some pathogens can also protect themselves, and they create immunosuppressive molecules that make your immune system chill out a little bit, which doesn't work for your benefit, that works for the infection's benefit, right? So if we're going to look at an infection from start to finish, right, we're going to check out an infection from start to finish. I'm going to use the flu as an example, right? So you've gone to work. It's your normal day at work, and you are stuck in the elevator with coworker Bob, and neither of the two of you are wearing a face mask. This is before COVID times, right? And Bob sneezed. How dare he? And he didn't even cover his mouth. How terrible of him. You're still breathing because you enjoy breathing. It's a good hobby to have, right? So you inhale that virus that Bob just sneezed. And as you inhale, the virus finds the cells that are along the back of your pharynx, along the back of your throat. And the virus can use its antigens to attach to those cells at the back of your throat. And the flu virus says, "Huzzah, I have a new home." Right? So the flu virus, using antigens, has found the cells with matching antigens that it can attach to, which happen to be the cells that line your pharynx. And the flu virus attaches to those cells at the back of your pharynx. breaks into those cells and starts turning those cells into virus-making factories for itself. So the cells at the back of your throat are no longer doing their own job, but they are making more flu virus. The first thing that happens, this flu virus has gone past the first level of your innate immune system. Because of your need and desire to breathe, you have inhaled the water droplets that came out of Bob's sneeze, meaning you have inhaled the virus beyond the barrier methods of protection and directly into the back of your throat. Right? So barrier methods of protection have already been bypassed simply by the nature of the fact that you were breathing. However, this is going to begin that second line of defense for your innate immune system. As the cells become infected with the flu virus and more flu viruses attach to more of your cell's antigens and break into your cells using that antigen attachment, those cells are going to start creating interferon. And your throat cells are going to start creating cytokines to warn their neighbors, hey, help, I'm being invaded. Call for help. This isn't right. Protect yourself with these interferons. It's too late for me. So one by one, the cells at the back of your throat are going to either start attempting to protect themselves with the interferons while making more interferons and calling for help with the cytokines, or they are going to succumb to becoming infected with the flu virus. Eventually, a natural killer cell that is in passing notices what is happening. He hears the cries for help, or the natural killer cell detects these cytokines and other complement proteins and chemicals that the cells are releasing, as well as detecting the interferons. Your natural killer cell identifies that these cells are no longer presenting self-antigens, they are presenting antigens for the flu. So the natural killer cell immediately begins taking out those cells, just commit suicide. You commit suicide. Commit apoptosis. And it's going to continue to spread the chemicals to the infected cells to make them commit apoptosis, or undergo the process of apoptosis. Right? In the meantime, this is also spreading more cytokines, and more signals are being sent out. This is starting your inflammatory response. So you have a little bit of fluid now swelling rushing to the area, which is causing some swelling in the back of your throat. This is painful, you're not comfortable, you are upset because you had a big project due for work, and it looks like this is not going to go well for you. Your throat is scratchy because your body is destroying the cells that were infected by the flu, and those cells are undergoing apoptosis and dying. You are losing cells and tissue at the back of your throat, and this causes you pain, plus the swelling. Things are not comfortable, right? Your inflammatory response has commenced. So your inflammatory response is causing the back of your throat to swell, and there's pain, as well as things are warming up and heating up a little bit. This is bringing more and more neutrophils and macrophages to the site of the infection, and they are swarming around, eating the debris and the destroyed cells from the natural killer cells, while simultaneously committing phagocytosis against any viral pathogens that they can find floating by. Right? And while they are doing that, the natural killer cells are seeking out more cells to kill, while encouraging the macrophages and the neutrophils to continue eating, keep cleaning everything. So your natural killer cell is releasing things that are making the macrophages and the neutrophils more and more hungry, or go faster as they are performing their phagocytosis and cleaning the debris, essentially, while eating the pathogens. Your natural killer cells are making them do it better, faster. Keep going. They're releasing chemicals that are sending them into a frenzy, right? All of the excess liquid that is coming from the swelling and the fact that you have cells that are dying, so you have some debris that needs to be swept away by this exudate liquid that's around, is going to be swept into your lymphatic system, go down your lymph vessels to your cervical lymph nodes, because this is all in the back of your throat, where B cells and T cells are going to begin, and other monocytes or macrophages are going to begin eating the debris and filtering your lymph, your extracellular fluid. Eventually, some of the macrophages that have been phagocytosizing all of your infected cells are going to ingest the antigens from your flu virus, and then they will create their MHC class II protein and present these antigens to a helper T cell. And the helper T cell, using an MHC class I protein, will identify the MHC or the antigen from the MHC class II protein, take it, and then your helper T cell is then going to run back to the lymph node, or float back to the lymph node in the exudate. And it is going to find a B cell or a cytotoxic T cell. And it is going to show these cytotoxic T cells the antigen. It will present the antigen that it has to the cytotoxic T cells. So the cytotoxic T cells with their CD8 receptors will read the antigen that your helper T cell has on the CD4 receptor. And then the cytotoxic T cells are going to travel through the lymph and blood vessels toward the back of your throat, specifically seeking out to destroy flu-infected viruses and flu-infected viral cells. In the meantime, your helper T cells are still floating around the lymph nodes, and they are seeking out a memory cell. Once they have found the memory cell, the B cell that corresponds to this antigen in this flu, they present the antigen to this memory B cell, and that memory B cell grows, multiplies, creates clones of itself. Those clones become plasma B cells, begin making antibodies against this flu virus, and over the course of the next few days, you're going to have a massive antibody response against this flu, where your system is swept with antibodies to protect you from this illness. If your helper T cell cannot find a memory cell that knows what this version of the flu was, it's going to assume that this was a primary response. So then it will take its antigen to a naive B cell, present the antigen to this naive B cell, and then that naive B cell will take the antigen and over the course of the next 3 to 6 days create an antibody to that antigen, and then begin to grow, divide, create plasma cells that make more antibodies, and then spread the antibodies that will stick onto these viral flu-infected cells to flag them so that your cytotoxic T cells and natural killer cells can kill them faster and better, so that you get over the flu better. In the midst of all of this, as your cells are dying and your macrophages and neutrophils are feasting on the viral infected cells at the back of your throat, they are releasing pyrogens, which is resetting your body's thermostat to up your metabolism, and you are starting to have a fever. So your body temperature is now rising. By this point in time, you are in day 3 of full primary immune response. You feel absolutely terrible. You have chills from your fever. You're stuck at home in bed drinking orange juice until the next few days ride out. And then when your immune response starts to taper back down, when there are no more viral infected cells for your immune system to kill, you'll get better and go back to work. And that is your pathway talking about this from the more anatomical perspective that we've been discussing. On the flip side of things, if I'm going to tell this as a story, right? Bob sneezed on you, and the flu was evil and wanted to infect your throat cells. So the flu virus began to infect your throat cells. And as your cells were becoming infected, the cells started screaming to their neighbors, "Help, we have an invader. Help, help, help. Save yourselves. Use these interferons and tools to save yourself. I'm done for. I don't want any of you to be taken out by this virus, so I need to off myself." And the cells at the back of your throat start screaming for help while killing themselves. In the meantime, this calls the attention of Border Patrol, your natural killer cells, that come by and see that there's a lot of people screaming for help because they are becoming infected, just like a zombie apocalypse. Your Border Patrol says, "Oh no, this is not going to happen on my watch," and starts killing infected cells and making the infected cells commit suicide before they can do damage to your body. He calls for backup in the form of the normal police officers. And normal police officers, your neutrophils, and the SWAT team, the macrophages, rush in and arrive. Natural killer cell is still calling for backup, and he's going into full panic mode. So the cops and your SWAT team also go into panic mode, and the more they kill, the more frenzied they are for the neighborhood that is the back of your throat. In the meantime, all of this is releasing, all of this are releasing those pyrogen proteins, which is heating up the environment and the temperature. You are gaining a fever. Some of your SWAT team members, those macrophages, are like, "Nah, we're not going to do this for long," and they go full sociopath, and they start taking the skin of the enemies that they kill, and they begin to start presenting them to other military officials. Like, "Sir, I have the skin of our enemies in my hands here. Take this, use it for what you will, make wanted posters, this is the enemy." And then your helper T cells, which are your first-line army cadets, take the skin of the enemies and say, "Yes, I will deliver this to everybody who needs to know." And your helper T cells, like good army soldiers, run to the Marines, who are your cytotoxic T cells, and say, "This is the enemy, go kill them all." Cytotoxic T cells say, "Right on it," and they get gone killing the enemy, right? And then your military officials, your helper T cells, run to the CIA and say, "CIA, like, intelligence, this is the enemy. Give me all you got against this enemy." Your B cells, being good little CIA, like, intelligence members, then take the skin of the enemy and start doing their research into it. If they have seen this enemy before, they will find the specialized sergeants that have seen this bad guy before. Find them, ask them, "What weapons do you build, and did you use against this?" That sergeant will begin building those weapons, the antibodies, will tell others how to build those weapons and antibodies, and your body is going to mount a harsh response against these enemies. If this is a new threat, you've never seen this group of terrorists flu virus before, you're going to create a new weapon against them, give it to new members of the CIA, they will create a new weapon or new antibody against it, and some of them will remember how to build this weapon and will store the blueprints for this weapon for later use 10 years down the road in the filing cabinets within the lymph nodes. They're going to start issuing out these lovely weapons, and they're going to start issuing out these weapons, coursing them through your system, And these antibodies are going to come attached to the viral infected cells to flag them for death and to slow them down. And then your Marines, those cytotoxic T cells, as well as your natural killer cells, will see that they are slowed down and flagged and take them out like good military personnel do. Right? And eventually, the fever will subside. All of the flooding that they did to cause the area to be cut off from other regions so it wouldn't spread will wash away back into the lymphatic system. That's the exudate, or exudate from the swelling and immune response. Eventually, your fever will subside, and you will go forward in life. Those are your two options for full immune response, right? So I hope that made it make a little bit more sense to you. That being said, that doesn't mean that things always go correctly and always go off without a hitch when you get sick. Right? And I know that being sick means something has gone wrong in the first place, but sometimes you can get sicker than other things, right? So, last video, I told you to remember some key things, right? About immunicity and deficiencies and that kind of thing, right? HIV is a prime example of things that can go super wrong, right? So HIV, well, we've been talking about the flu virus. Your flu virus attacks the cells that are at the back of your throat. They attack the pharynx cells, right? That's why you get a scratchy throat when you have the flu. HIV does not attack your throat cells. The antigen that HIV attaches to infect cells is that CD4 protein. It's the CD4 antigen. That means that HIV specifically targets your helper T cells. If you remember from the chain of command that we've just gone down, the helper T cells are the cells within your adaptive immune response that talk to both the adaptive immune system, that phase 3 of defense, and the phase 2 of defense, the innate system. The helper T cells were the ones that were taking the antigens from the antigen-presenting cells like your macrophages and bringing them to the assassin cytotoxic T cells, right? If you don't have the helper T cells there, you don't get an adaptive immune response. All you have are your first two waves of innate immune response. That's what's so deadly about HIV. It attacks the helper white blood cells and breaks down that line of communication. Right? So what happens here with HIV, it will break that communication down. And without that, when your count of helper T cells gets too low, we say that you have gone from having HIV, or human immunodeficiency virus, right, to having full-blown AIDS, which is autoimmune, it's your autoimmune, oh Lord. Autoimmune deficiency syndrome, right? Because your autoimmune system is deficient and it can't work anymore. That's why AIDS can be deadly. And the bad thing about the HIV virus, or human immunodeficiency virus, is it mutates very quickly, right? Which is why individuals who have HIV have to change medications every 6 months to a year. Because if they stayed on the same medication for 2 years straight, the HIV that they have would become immune to it, and then the HIV would kill them. And inevitably, eventually, That is what happens with individuals that have HIV, and that's how they die from it. Technology is getting better. It's not the same death sentence that it was in the 80s. And now by switching medications, we understand a little bit better by switching medications more frequently, right? And by using our more advanced modern methods to help with this illness, individuals can live for decades with HIV now. But once you're on that downhill spiral where you are indeed, where the virus in you is indeed has mutated to be immune to all of the known medication that we have, you're going to go downhill rapidly, sadly. There has been improvements with discovering this kind of thing, though. I will give hope for that. They have new treatments for this now that are coming out. So much so that seem to be so promising, and so many people are living more long-term with HIV now that we're talking decades instead of like a year or two, like like what happened in the 80s when HIV first struck the United States in a big way. The CDC was contemplating a few years ago downgrading AIDS from a terminal illness into a chronic illness, which is like the same kind of ranking that you would give something like diabetes, which is something that you're going to have the rest of your life. It will probably kill you, but you can live the rest of your life with it, right? But they have not downgraded its terminology or ranking yet. Part of that is probably the history associated with the disease. The other part of it is probably because the medications are just not that advanced yet. But we are making progress with HIV. If you choose to work at Grady Hospital has they have a clinic for HIV patients in Atlanta, and they are one of the few hospitals in the area that have a specific HIV clinic within them. Something to know and options to understand to go forward in, right? Remember how much talking I did, right, earlier about, well, we'll talk about sensitivity first. Some people have more sensitive immune systems than others, right? Your IgE proteins, for example, these receptors on your mast cells, are going to create slight more sensitivity toward illnesses and whatnot. When IgE is bound to mast cells, you're going to get sensitization to things. This can range from mild to severe, right? You know this kind of stuff as an allergic reaction. If your body has become hypersensitive to a certain type of antigen, and these IgE antibodies start triggering your mast cells or basophils to create more and more histamine because bad things are happening, this is going to be the type 1 here is going to be a massive allergic reaction, essentially. This can range to, you get a lot of hives and whatnot and turned red, to, oh man, your body thought that peanut dust was absolutely going to kill you, so your body, to protect your immune system, to protect yourself from that peanut dust, is going to shut everything down to prevent the peanut dust from getting into your system, which is what anaphylactic shock is, right? Anaphylactic shock is such a severe allergic reaction that your body has shut down your ability to breathe in and breathe out because it doesn't want to breathe in or out the pathogen, or what it deems a pathogen. But the problem with that is sometimes, depending upon what you're allergic to, that pathogen is a peanut. Or the pathogen may be a bee sting. Something like that, right? But anaphylactic shock is what happens when you are when your immune system is way too sensitive to a trigger and it goes off, right? You can also have other types of hypersensitivities, type 2 and type 3, right? You can have vascular issues with type 3, right? This means that something is going on here that is making you have an inflammation response when you shouldn't necessarily be having. So this is like complement protein activation. Remember how I was talking about sometimes the complement proteins will attach to things that shouldn't necessarily cause a problem, but they do? Like makeup and that kind of thing? This would be that kind of hypersensitivity to something weird along those lines. And that is causing your immune system and your inflammation response, your neutrophils and more neutrophils and macrophages to respond to silly things that they shouldn't be. Type 2 hypersensitive stuff would happen if you have a mismatched blood transfusion, right? So cells are being destroyed here because somebody made a mistake and they've activated each other. Maybe this is an Rh factor type issue, where during the birth of your child, your body discovered, oh, the infant has a positive blood type and I have a negative blood type. We have to attack this in the future, and your body begins attacking future pregnancies. If you put A blood inside a B blood person, mismatched blood types, this kind of thing would be a type 2. And then you can also have delayed hypersensitivity, which is a cell-mediated response, right? That means that it's going to allow cytotoxic T cells and macrophages to accumulate at the site of infection because they have a delayed response system, which can cause a contact sensitivity, so everything kind of hits all at once when things do hit, if they do hit, kind of deal. So you can be hypersensitive to things. Your immune system could be way too ready to act too severely, right? And remember how most of the things I've spoken about relied on your immune system to be self-aware and not attack yourself? Your body does a lot of double checks to ensure that your immune system tolerates your own cells. Some people drew the short end of the genetic stick, or something went wrong in their body, right? Something cross-linked with an antigen and is now causing badness. Somebody, like there was a bacterial infection that used a similar antigen to the stuff that's in you, right? Some evidence multiple infections may prevent autoimmune diseases, genetic factors. For whatever reason, your own immune system is going to start attacking your cells or specific sets of cells for things. These are called autoimmune disorders, right? Sometimes they can be super simple. Like this little bullet here says sometimes bacterial infections may cross-link with a self-antigen. The best example of this was in like all over Facebook and the news a couple before COVID, right? Like a year or so ago, with the Lone Star ticks making people become vegetarian. I know that was weird. I know that sounded weird, and you probably saw the posts on Facebook and you were like, what is this nonsense? But what tends to happen is when a Lone Star tick bites an individual, or when any bug bites you, what is going to cause the itch that is caused by bug bites is the fact that the bug is backwashing some of its spit into you. I know that is this terribly gross and disgusting, and you're never going to be bitten by a mosquito again. But if that happens with Lone Star ticks, something in the Lone Star tick's saliva or spit, as it's backwashing into you, is a similar protein to the proteins that are found on red meat. So most meat, like pigs, both pork and beef, that's not chicken, right? And if you are bitten by enough Lone Star ticks, like let's say you just live out in the backwoods and you love going deer hunting, so inevitably you're going to get bitten by a few ticks every so often because you're out in the backwoods deer hunting. If you are bitten by enough of these Lone Star ticks, every time you eat red meat after that, your body is going to have an immune response to that meat as though you're allergic to it, because it's going to respond to that the same way that it responded to the tick bite. Right? Meaning that eventually sometimes people are actually going to have to stop eating steak and that kind of thing for those poor people. That's why it was in the news a few years ago. There are some genetic factors here, like this picture here. Do you see how jacked up these fingers look? Right? This poor person here, right? Your fingers are not supposed to be bent off to the side like that. They're supposed to go straight up and down. You guys can hold up your hand to your screen looking at these pictures and see how bent these fingers are, right? That is something called rheumatoid arthritis. That is a type of immune deficiency or autoimmune disease where your immune system, for whatever reason, probably genetic factors, but for whatever reason, your immune system has decided that your joints are not you. So your immune system is attacking your joints, which causes them to swell and the bone to build up more, and your joints are going to get stiff because of it. This is what rheumatoid arthritis looks like, right? There's a whole host of problems and causes for different autoimmune diseases. You guys have heard of some of these. We talked about Graves' disease a little bit with your thyroid receptors and your thyroid problem with hyperthyroidism. But Graves' disease is caused because your immune system is attacking your thyroid and making it work too much. On the flip side of things, if you end up with hypothyroidism because your immune system is killing your thyroid, you may end up with Hashimoto's disease or Hashimoto's thyroiditis. Lupus, if you ever watched House, he's always saying it's never lupus. Lupus is a disorder where your immune system is just picking off organ systems to attack. That's why lupus can be deadly. Type 1 diabetes, this is children's diabetes. If your immune system is attacking the beta cells in your pancreas as a child, you're going to develop type 1 diabetes, meaning you're not going to be able to make that much, if any, insulin. So you're not going to have good sugar regulation, and you're going to be a child with type 1 diabetes that needs to take insulin. Celiac disease means that your immune system is causing damage to and inflaming your small intestines whenever you eat something called gluten, because of a protein or enzyme within your digestive system called transglutaminase, right? Gluten, by the way, because this is a fantastic buzzword now, celiac disease is real. It means your immune system is attacking your intestines because you ate stuff with gluten in it, right? We are more considerate of this, and this is also part of a dieting bandwagon in the country right now, because gluten goes hand in hand with carbs. So people are trying to cut gluten from their diet and all that kind of stuff. Gluten is a protein that is created when you mix flour and water. So you can find gluten in any bread product like bread, pasta, that kind of thing, right? So if you're going on a low-carb diet, you're cutting, by nature of that, you are also probably cutting a decent amount of, don't get me wrong, if you're going low-carb diet, it also means you are cutting back on simple sugars like candy bars. But gluten is a complex sugar, and you are probably also backing off on your gluten intake as well. So low gluten diets go hand in hand with low carb diets. People tend to conflate the two. But it is possible to have celiacs and cut gluten out of your diet, but not cut carbs out of your diet. Also, read labels for food and that kind of thing before you buy. Just a straight up warning. I have seen grocery stores put gluten-free stickers on bottles of water and then sell those bottles of water for 3 times the cost that the rest of the water is. Water doesn't have flour as an ingredient in it in the first place. There's no reason to buy gluten-free water bottles. Water bottles are supposed to be gluten-free anyway, unless you're just sprinkling flour in there for whatever reason. So, know what you're buying and know where gluten comes from if you're going to buy into any of that kind of stuff. Right? That's my fair warning about that. Don't be taken for a ride by, current dietary fads that people take advantage of. But yeah, these are different autoimmune diseases that can happen when things go wrong. Right? remember how I mentioned that MHC class proteins and other things are specifically for you and no one else? This is why whenever you need a transplant, they have to do lots of testing for tissue typing and histocompatibility. Do you have the same type of antigen proteins on your organs that this individual needs so you can donate a kidney to them? That kind of thing. It's possible to have multiple MHC class proteins on one cell. That's Mhc Pylogeny Polymorphism for MHC polymorphism is when multiple alleles for each MHC locus. That's a genetic thing. If they are irresponsible and they put somebody's organ, like they give you a kidney and you didn't fully match the MHC class proteins, your cytotoxic T cells are going to mount a massive immune response to the newly implanted organ, right? Within the first couple weeks of a transplant. They are going to put you on immunosuppressive drugs to help this not happen, but if they didn't match the MHC class proteins beforehand, that's going to take priority. If they match the MHC proteins and then they put you on immunosuppressive drugs after a transplant like they do, you are more than likely going to be fine, right? Yeah. And that's your immune system, ladies and gentlemen. If you have any questions, let me know.